Hello everyone, and welcome to AISC's webinar, Structural Fire Engineering, presented by Alan Jowsey. Today is June 4th, 2015. My name is Christina Harbour. I am with AISC's Continuing Education Group, and I will be moderating today's presentation. I want to thank everyone for joining us today, but before we get started, I have a couple quick announcements. Here's how the webinar format works. All participants will be in a listen-only mode for today's presentation. Hopefully you noticed that you have the option of listening through your computer, streamed over the internet, or through the phone line. You will have that option throughout the presentation. Should you experience any technical difficulties with the streamed audio, you can always switch over to the phone. Depending on the speed and quality of your internet connection, you may find that listening to the audio through the phone may eliminate any perceived delay between the slides and the audio. Again, everyone is in listen-only mode. However, as advertised, this live webinar will be interactive. You can submit questions at any time by typing them through the chat feature located on the left of your screen. Questions will be addressed as time allows, but our intent is to answer questions during the presentation. Also, please resist the urge to use the raise hand feature. Just type your question into the chat. For legal reasons, I must announce that today's presentation is being recorded. AISC is a registered provider with the American Institute of Architects Continuing Education System. It is our intention to fulfill AIA's requirements with today's presentation. Additional information, including the course description and learning objectives per AIA's requirements, can be found in the handouts. This information was also displayed leading up to the start of today's presentation. And a note on CEU credits. Within 2 days, you'll receive an email with information on how to obtain your CEUs. This email will come from registration@aisc.org. Please follow the instructions that will be provided in the forthcoming email. There will be an online form. You can obtain CEUs for everyone at your connection. Look for the email no later than Monday evening. Again, coming from registration@aisc.org. Handouts have been made available for today's presentation. We certainly encourage you to download the handouts for future reference. And with that, I want to introduce today's speaker. Alan Jowsey obtained a PhD in structural fire engineering from the University of Edinburgh in 2006. He worked as a consultant fire engineer in London for several years and now leads a global team of structural engineers and fire engineers within AkzoNobel's Fire Protection Division. Dr. Jowsey sits on numerous global technical and standards development bodies, including the ASCE SEI Fire Protection Committee. His work involves overseeing research and design activities while also generating practical solutions through liaisons with engineers, contractors, and steel fabricators around the world on projects in the built environment and oil and gas markets. And with that, I will hand things over to Alan.
Thank you, Christina. And good afternoon, ladies and gentlemen, and thank you for your time, and thank you to AISC for this webinar. So hopefully this webinar will give you an overview of some of the aspects in relation to structural fire engineering. I'm conscious that some of you on the webinar will have some experience in this. I'm also conscious that this could be a very new topic to a lot of you. So hopefully the content that you see today will cover some of your expectations with respect to the overview that's already been provided. If I move on to the first slide, we have a very quick agenda, so you'll see the course of the webinar as it flows. We're going to start with a relatively high-level overview on fire engineering to introduce what it is, where the markets are for it, some of the key drivers and considerations that go through the thought process with respect to fire resistance. Then we'll move on to some of the more fire resistance related topics, looking at the fundamentals. Where do passive fire resistance ratings come from, and what are the options to do to achieve fire resistance of a steel structure. Once we've established the fundamentals, then we're going to move on to look at some of the more challenging concepts, the structural fire engineering in more detail. We'll go through some of the methodologies that are employed, and we'll go through some of the benefits and the optimization processes that can be used on projects on a day-to-day basis or on specialist, perhaps iconic buildings. And finally, the best way to really illustrate this is to do this in terms of worked examples with respect to what I would call basic fire engineering approaches, and then bringing more of the structural engineering aspect into that. And we'll finish up at the end with a quick recap and a summary of what we've been discussing. So, overview of fire engineering to begin with. And as we go through these slides, I'm going to draw on some of the experiences that I have certainly from within the industry, both within the built environment onshore and the oil and gas industry, which I deal a lot with as well, and some of the interesting relationships that occur between them. So what is fire engineering? To many people, fire engineering carries different concepts and different meanings. My own personal way of summarizing this, I put in the top sentence in italics at the top there. Fundamentally, it's the use of science, engineering, analysis, and underlined there, common sense to provide fire safety precautions tailored to a building. It's performance-based design, if you like. It's looking at the risk of fire that can occur in a structure and designing with respect to that. And I put some key bullet points down there, some of the things that may be associated with fire engineering. The management aspects, the evacuation side of things, fire modeling leading on to smoke control, aspects of heat transfer, and structural fire engineering. It's the main structural fire engineering and heat transfer elements that I'm going to focus on today from a structural perspective. So some of you, as I said before, may have some appreciation or understanding of what structural fire engineering is. Summarized very quickly, if you have a fire load, let's say it's similar to a structural load that you may consider, you've got your loading scenario. If you then do heat transfer, you understand how your structure heats up, and then you can perform a structural analysis to understand the response of your structure at elevated or high temperature. So you have your fire, your heat transfer, and your structural analysis. And to many people, structural fire engineering, when it's mentioned, it sets certain words ringing in people's heads, if you like. And I've listed some of them here. Some of them associate it with a very specialist aspect, and only certain key people are undertaking this work. Some people refer to it as being very complex, very advanced, very expensive, time-consuming with respect to approvals, if you like, which can be the case in certain aspects, but not always, as we'll see in this webinar. Other words that we see floated around with respect to structural fire engineering are very much in respect to cost savings and money. For example, a design could progress through past detailed design to tender documentation and tender procurement. And at that point, people start to look at costs with respect to budgets. And then they start to say, well, what can we do in terms of value engineering? How can we optimize and bring cost savings to this while still maintaining the required standard for safety? And that's not always with respect to fire engineering. That happens at all aspects. I'm sure you're aware on your relevant projects on a day-to-day basis. So moving on to the next slide. Typical markets. It was mentioned in the overview of my background that I work in both the oil and gas markets, onshore and offshore, together with the built environment. And these are really the key areas for markets like this. I put some typical pictures on there. Onshore, we're looking at things like commercial offices, hotels, airports, stadiums. And then going offshore, it can be anything from vessels, storage tanks, oil rigs, floating platforms, ships. Fundamentally, wherever there's a risk of a fire in close proximity to a structure, then fire resistance should be considered at some point in the design. And what are some of the benefits of doing this? Well, we touched on it earlier. Cost, and it undoubtedly is one of the key reasons for doing this. But also looking at things like robustness. That's very important, maintaining acceptable levels of safety. Often structural engineering approaches can be used to permit more innovative and complex buildings, which were not necessarily possible due to prescriptive natures of some codes. For example, very long span beams or truss systems, which when we try to correlate what we test in a furnace on a short scale, and we try to look at the understanding of performance at long scale, becomes a little bit more different. But architects these days are very keen to look at big open plan floor spaces, long span members, and it's trying to combine that innovative design together with structural analysis at high temperature, together with robust design, which is very important. Also on the issue of robustness, this approach can be used to identify and strengthen, if you like, weak links in a structure. So if we do a design at ambient, everything seems to work fine, we're happy with it, the structure stands up. If we look at it from a thermal, high temperature perspective, then it's not implausible that we could identify some weak connections. We could look at columns or beams or actual connections and joints that need strengthening. As things expand due to heat, it generates all sorts of strange forces which need to be considered. Likewise, as steel members start to cool, they generate contraction forces, and that can generate all sorts of redistribution which should really be considered in a fire. Moving on to the next slide. Just a little bit slow at my end. With this, we're currently on the agenda page. We're going to try and move forward. Okay, so the slide that you see in front of you right now is global acceptance. I mentioned before that I have a global remit. I work on projects across the world, and I just wanted to share with you a bit of a flavor of what goes on in different areas, because it does change with respect to location. Structural fire engineering has a large dominance out of the UK. There's a lot of practices that seem to work. We seem to find that within UK and Europe, that understanding is quite good and it's promoted, and there's a lot of buildings which go through a structural fire engineering assessment. To the extent that, for example, many high-rise buildings in London, it's accepted that not only will you have a structural engineer working on the project, you'll also, as you'd expect, have a mechanical engineer, you could have an electrical engineer, and it's just accepted now that you'll generally have a fire engineer, and that some sort of structural fire engineering assessment will probably be undertaken. As we move around this clockwise, if you like, moving across to the China, Hong Kong, Taiwan region, as I've labeled it there, they have good potential. Essentially, anywhere you've got high-rise buildings, lots of steel work, then there's no reason why you can't look at some sort of structural fire engineering assessment. I've made a note there, China are about to release a new structural fire code and a fire test standard, which is going to be very similar, as we understand, to the European approach. In Korea, there's a huge demand in the oil and gas markets. There's an awful lot of offshore construction done in that area, and there's a big thirst for demand for optimization and structural fire engineering understanding. Down into the Australia, New Zealand, Southeast Asia area, again, a lot of high-rise buildings, an awful lot of construction going on, and there's an awful lot of interest in areas like New Zealand particularly as to how you employ and take benefit of fire engineering approaches. South America, very similar, potentially a very big opportunity there. A lot of oil and gas going on, as you'd expect, a lot of very good potential and demand, as there is in North America. Okay? And the reason for putting this up is just to let you know that an awful lot of good work is done in other parts of the world, and there's no reason why this sort of approach cannot be used in North America. Okay, if we look at the drivers for fire resistance, then there's two real reasons for doing it. And number one, first and foremost, is life safety. So life safety measures are considered mandatory by a lot of fire and building and safety codes. The evacuation of people and the safety of people in buildings has to be paramount. The second driver, if you like, is asset protection or property protection. We see a lot of requests now from building owners or asset owners where they say, yes, life safety, absolute paramount, but it's vital that my structure or my building or my business is not affected in the event of a fire with respect to loss of the total asset, loss of revenue through business, and loss of possible customers. In the event of a fire, they want to be able to reinstate whatever needs to be protected or repaired and ensure they can get back to business as quickly as possible. Okay? And how do they achieve this? Well, there's two fire protection measures really. There's one called active fire protection and one called passive fire protection. Active is similar to your automatic detection system, your sprinkler systems. It's anything which, in essence, will sit there and constantly monitor the scenario and the environment around it. And at the time of a fire, it suddenly kicks in and does its job and acts to either control, suppress, or alert something that something has changed with respect to fire. Passive fire protection, on the other hand, effectively, as I put there, remains silent within a building until a fire occurs. And I've put some examples there: fire barriers, fire stopping, steelwork protection. It sits there, and in the event of a fire, it just does its job without activating in any particular way. And many projects and clients that I come across in different parts of the world sometimes say to me, well, I've put active fire protection measures in, therefore I don't need to have passive fire protection measures. And that's not always the case. Really, in the fire safety strategy of a building, both active and passive protection measures are integral to the fire safety. Okay? The use of one, as I put there, does not negate the use of another. So, in our overview, if you like, methods and drivers. We'll get into the details of a little bit of these a little bit later on. But I've listed at the top corner there 4 different, what I would call traditional structural fire engineering approaches. The first one is a design fire assessment or modeling. That's understanding how a fire is going to ignite, how it's going to grow, how it perhaps will travel around within a building. And fire engineers will do this frequently using simple calculations through to more detailed calculations. The second one is elimination of fire protection from certain members. So, for example, there may be a localized fire which is impinging or having an effect on a specific portion of a structure, and therefore there's a justification to say that the structure away from that design local fire can be left unprotected. We also see a lot of requests now across the industry where members will be protected framing between columns, and therefore we see technical justifications put forward to say that the secondary members acting within the bay, if you like, they can be left unprotected due to the effects of tensile membrane action at high temperature. And I'll touch on that again a bit later. The third one is modification to fire resistance periods. This is a very common approach that's used across Europe and the UK. And this, for example, is taking a code-rated, say, 2-hour building and justifying why it can be a 90-minute building instead. And we see this very, very frequently. And the last one there is structural fire resistance checks, or what I call hot design. And it's very similar to ambient design that you do with respect for a column, for example, with respect to compression and buckling, or a beam with respect to overall flexural bending or shear capacity checks. It's very similar, it's just repeated at hot design, at high temperature. And we see requests for structural fire engineering approaches undertaken by some of the ones listed there in the bottom left-hand corner. Structural engineers are getting more and more savvy, and they're starting to understand what can and can't be done with limitations with respect to fire engineering. Fire engineers will obviously promote their services and explain what benefits they can bring. Main contractors are starting to understand how they can make efficiencies in construction sequencing and design methods by either reducing or eliminating the need for fire protection while still maintaining a robust and safe solution. Fabricators, again, if they have fire protection perhaps as part of their package, then they're starting to take a keen interest. And we also see the occasional request coming from applicators or installers of passive fire protection wanting to help within the design chain to value engineer and bring costs down. And I've touched on some of the words that you see in colour on the bottom right there. These are some of the reasons, if you like, why people would like to see a structural fire engineering approach. Cost savings, invariably, we can't get away from that. But robust design, quantified performance in the event of a fire is becoming more and more paramount within the industry. Construction sequencing, if you've got a reduced thickness, if you like, of fire protection, it's potentially quicker to apply, it's less time on site. Practical considerations, we see requests for engineering approaches when things happen on site, and sometimes the contractor comes and says, this can't actually be physically achieved. Do we really need it? By code, yes, but when we start to look at the risk of fire and what can happen, then we can put a technical solution forward with respect to that. And sustainability benefits, of course. Less material, fewer coats perhaps, or fewer volumes or mass of fire protection, reduced materials have sustainability benefits. So considerations and basis. We've touched on the high-level overview, if you like, for fire engineering and what it gets involved. Now we're going to delve a little bit deeper and take it further. A simplified overview of the contract chain on the right-hand side that you see there. We start off with the schematic design or concept design, and move all the way down through construction documents, bidding, and occupancy at the end. And through experience, I know that fire resistance is typically defined early in a project, i.e. the hourly rating, but the fire protection to achieve that often comes as an afterthought of design. And hopefully one of the outcomes of this webinar that you'll see is that the earlier it's considered, the greater the benefit that can be had. So some basic concepts. Simplified diagram here to look at three different aspects of fire resistance. If I've got a fire acting underneath a slab in this case, then I'm going to be checking for three different things. Starting bottom left, I'm going to check resistance to flames and smoke. Essentially I'm saying I don't want cracks to open up and for heat or smoke to pass through and cause multiple floor fires. So I don't want fire to spread from the floor below to the floor above. Transmission of heat should be limited, illustrated by the fried egg on top there. So if I've got a fire underneath, then I don't want excessive heat to transmit and conduct through that slab to cause a fire of potential combustibles on top. And the last one is that the structure should not collapse. So for the given applied loading, the structure should be able to get to a certain temperature but not collapse. And that's where we're going to focus the remainder of this talk on today. So some very simplified concepts. What happens when a structure heats up? Consequence of failure. So I'm going to start off with beams. The simplified diagram shows there that if I heat a beam up, then it's going to start to expand. Okay? As steel gets hot, it expands. In this case, you might get to see some sort of deflection. It may start to bow down. Doesn't necessarily mean it's going to collapse. Sometimes a large degree of deflection can actually be tolerated at high temperature. And it doesn't matter where that is. It could be high in the building or low down. The scenario is pretty much the same. However, if the thermal expansion or contraction forces are too great, then we could lose the joint. The joint could collapse and give way. And in that situation, on the right-hand side that you see there, you then have a long column or a tall column which is unsupported over a large length, and then that's at risk of buckling failure. Columns are a lot more critical. If we have a fire which impinges or impacts a column to the point where it's going to lose structural stability, then as you'd expect, the consequence of failure of that could be very large. And it doesn't matter where you are, either high up in the building or low down, it's pretty disastrous if that's going to happen. So deliberately simplified, but just to illustrate what can happen and to get you thinking. And it's not only looking at single element members, if you like. We can also look at the concept of disproportionate collapse, which I know that many of you will consider in your day-to-day designs. And the concept is very similar when it comes to fire resistance. In this case, you can see that the blue triangles represent the load being carried by the columns, the internal columns carrying, in this case, a little bit more than the external columns. But suddenly I have a floor fire which is starting to affect my structure. What happens is, in this case, we've got the column losing its capacity and the whole building starts to collapse. The forces get redistributed out to adjacent columns, and that fire may continue to grow and spread over the floor plate to the point where adjacent columns go and the force again gets redistributed, and so on, for disproportionate checks. And the same approach can be done at ambient as for fire. You can do redundancy checks. If you feel that a column or a particular part of structure is vulnerable to the effects of fire, then you can use an ambient model perhaps and just do element removal as a simplified check to see whether it can still stand and the redistribution of forces can be carried by the structure. So, to get you thinking a little bit more, I've got an example here of a connection design. And I've done it in terms of ambient design and fire design. Let me talk you through this. If we start with a structural design, a structural model of a building, then generally the connections in a certain model would be idealized. So pinned connections, for example, or fully fixed, or carrying some proportion of moment. The structural engineer will then take the forces acting at the ends of the member and pass those to a specialist to do the connection design, or they may do the connection design themselves. It depends on the engineer and the practice. But what they're doing is they're taking a simplified approach. They're taking out inputs to be used in a more detailed analysis, in this case the design of the connection, which incorporates more detailed checks. I've listed there: bolt spacing, direct shear, so on and so on. So there's a lot of very good work, a lot of detailed work done at ambient. When we take it to fire, to high temperature, then I put straight away a question mark. And people say, well, I assume it's okay. It works at ambient. I've requested, in this case, some sort of applied protection to keep it cool. Therefore, I assume it works. There's a lot of assumptions when it comes to fire. And then I put back to a lot of engineers, well, what about things like this? What about loss of bolt strength? As steel heats up, it loses strength. What about ductility of the bolt and the connection plates? As steel heats, it becomes more ductile. So who's checking the bolt? Who's checking the plates of that connection? And who's checking heating forces and cooling forces? The thermal expansion effects and thermal contraction effects. These can be very significant in beams. And what I'm trying to illustrate with these 2 points here is that there's an awful lot of good work done at ambient, but when it comes to checking fire, checking structural stability here, perhaps it's a little bit too simplified. It may be okay, but fundamentally it's always best if the design responsibility, including hot design, falls within your remit, to have an awareness of this and to be maybe asking some questions or at least giving it some due consideration. So how do we achieve fire resistance? For many steel members, it's unlikely that they will have an inherent fire resistance greater than, say, about 20 minutes. It does depend on the section size, so very thick, stocky sections will have a higher inherent fire resistance rating than a very thin, slender section. But let's take the example of a building at 1 hour or 90 minutes. It's unlikely, extremely unlikely, that it's going to have inherent fire resistance without some sort of protection. So we have to put some sort of material on there to maintain its structural stability. And how do we achieve that? Well, there's a number of proprietary systems out there: intermittent coatings, boarding systems, cementitious coatings, or SFRM, as I know you commonly refer to them in North America, insulation blankets, bolt caps for looking at bolt protection, or concrete filling of tubular members or concrete encasement of, for example, in this case, I sections. There's a vast range of options available, and there's different reasons as to why you may choose one over another. So, let's delve a little bit further. Let's consider some of the codes and standards. Where does the fire resistance rating actually come from? Well, there's a wide range of international fire safety codes that help designers design buildings, and I'm sure you'll be familiar with some of the ones on here. The NFPA standards, the IBC, the International Building Code. And I just put down a couple there that we use here in the UK, for example. But I work in countries all around the world, and I get to understand all these codes inside out and what the similarities are and what the slight differences are. So somewhere within this code, let's take the IBC as an example, it'll tell me how much fire resistance is required for my structure. And alongside that statement, it'll say whatever assembly that I'm using to build my building should really be tested and should have test evidence with respect to a specific test standards. And I've listed those here. And these test standards fundamentally put that assembly into a furnace, subject it to a temperature time regime, so they heat it up over time, and monitors temperatures, deflections, stresses and strains. And if a proprietary system on a piece of steel, for example, can pass that, then it gets a certificate to say, yes, it's good for its purpose. In North America, we use ASTM E119, UL263 testing. In the UK, I've listed there BS476 is our test standard, and so on through mainland Europe, Australia, China, Russia. Functionally, these tests all around the world do exactly the same thing. They're very, very similar. They all have the same intent for design. They all heat the assembly to essentially the same or very similar thermal exposures. So let's look at the fire resistance rating a little bit closer. And I'm going to take an example from a couple of different standards. I'm going to start with one from the UK just for an awareness and appreciation only, and then we'll look at one relevant to the IBC. This is a table from British Standard 9999, and it's a simple lookup table, and 99.9% of fire resistance ratings around the world are done using a table similar to this. It's a very simple 20-second lookup, and in many cases that's it. For that aspect and that remit of work, it's done. No more consideration given to fire resistance. The ratings that you can see here are based on occupancy use, so the risk of fire. For example, is it an office with table and chairs, or is it a petrochemical facility? Is it an industrial facility? Is it a sports stadium? Is it a library? What is the risk of fire? Then the height of structure becomes very important for evacuation of people inside, and also for access for firefighters trying to tackle the fire. And it also makes assessment or provision for a suppression system, a sprinkler system, which may act to control a fire. And really I've tried to illustrate it here with the red highlights showing as an example an office building, 100 meters high, with a sprinkler system. And you can see there that the arrows pick up all the relevant inputs and focus in on a value of 120, so 2 hours. And in fact, 2 hours is the most common highest rating that we see here in the UK. And it's very similar when it comes to the IBC NFPA approaches. They also look at the intended use and occupancy. They consider the building area and the building height, accessibility for the fire department, distance from other buildings, and suppression systems and construction materials. And there's a statement actually in IBC which is in italics at the bottom there, where it says the structural frame is considered to be the columns and girders, beams, trusses and spandrels having direct connections to the columns and bracing members designed to carry gravity loads. And it's that last sentence, gravity loads, which we'll touch on a little bit later with respect to load combinations and degree of load acting on a structure. So let's take the same example, that 100-meter high building, 328 feet, 25 stories, and it's an office building. So within the IBC, it's identified on the left-hand side there as Group B for business. And then I know it's a steel building in this case. I know it's going to be a non-combustible item, so we're looking at Type 1 or Type 2 construction at this stage. So further using the IBC, I've got a further table. In this case, I've highlighted the row which is with respect to B for the business group. And then you can see along the top it's got types of construction, Type 1, 2, 3, 4, and 5. And then in the table itself, you'll see two numbers. The top number is the number of stories, and the lower number is the square feet of a building. Okay? So in this case, I know that it was 100 meters or over. It was over 300 feet high. It was over 25 stories. As I look from right to left along row B, I look at the number of stories, and I can see that when I get to UL, which means unlimited, then I can go to that one. So I'm focusing in now on Type 1, Type A. If it was Type B, then I'm only permitted to have 11 stories in the building. Now you can use a fire safety suppression system to make modifications in some respect to fire resistance periods. We'll look at that on the next slide. So I now know that I have a Type 1A structure for my office building, which is over 300 feet high. So the final table I look at in IBC is this one. And again, I've highlighted Type 1A. I've looked at the structural frame, which says I need 3 hours. And the floor construction, including supporting beams and joists, 2 hours. Below that, the roof construction, 1.5 hours. I put a note at the bottom to say for high-rise buildings where sprinklers are provided, then reductions in fire resistance ratings, so looking at reduction from Type 1A to Type 1B, for example, may be permitted in certain circumstances. I won't go into the details of that just now, but you can look at the relevant section of the IBC for details on that. So for my tall building, I have 3 hours for the structural frame, 2 hours for the floor construction, and 1.5 for the roof. That's in comparison for interest for the UK example, which would say all 2 hours. And then on top of that, fire engineers in the UK will invariably engineer down from 2 hours to 90 minutes on a high-rise building, providing they can justify it. So many people say to me, yes, the North American codes, IBC, they're very prescriptive in their nature. And they can be, but they also allow performance-based design. They allow prescriptive and performance-based fire-resistant designs, although the emphasis, as I put there, is primarily on the former. And I've lifted some of the text from the IBC on the right-hand side, which says alternative methods can be used, and it has the provisions under which that can be done. As long as you're meeting the criteria and exposure defined by the ASTM E119 standard, then greater flexibility can be provided. And we do see these around the country in the States and Canada, and we do see these applied. So fire resistance ratings. It's a little bit of a bugbear, if you like, of mine, pet hate, and I talk to a lot of structural engineers, and I say to them, tell me what a fire resistance rating actually is. And they look at me and they say, well, it's an hourly rating. It's 1 hour or 2 hours. And I say, okay, fine, let's assume it's 2 hours or 120 minutes in this case. What, though, is the acceptance criteria? At 2 hours, what should or shouldn't happen? And then I get different answers back to that, but generally along the lines of, well, the structure shouldn't collapse. It should maintain its stability. It should be able to still carry its applied load. And that's fine. When I say, well, how do we do that? And I get a lot of blank faces looking back at me. A lot of structural engineers have an appreciation of fire at a very high level. Some better than others, granted. But in many cases, a lot of structural engineers I speak to say, fire resistance or the hot design, it's not within my remit. I'm not being paid to do that. It's the responsibility of the architect. But when you start to look at responsibilities and some of the technical aspects that are required when you look at fire resistance, then there is an aspect of structural analysis which can and perhaps should be done. And the structural stability is really defined in terms of a maximum allowable temperature, or I've called it a limiting steel temperature. And I've put some examples that we see down there. In North America under ASTM E119, then we seem to see columns are limited to 538 degrees Celsius, which is 1,000 degrees Fahrenheit, and beams with a concrete slab on top are permitted to get to 593, which is 1,100 degrees Fahrenheit. For awareness, in Britain and the UK, we'll limit hollow sections or pipe or tubular members to 520, I-section columns or wide flange columns, if you like, to 550, and beams supporting a concrete slab to 620. In mainland Europe, they play even safer and they say nothing is permitted to exceed 500. And then if you go offshore, they'll say nothing should go above 400. And really the derivation for that is really based on limits on permissible stress, allowable strength design, and designing within elastic limits. But the industry has put a number of messages out there to say that really these temperatures are generally acceptable for most circumstances, but not always. And in a lot of tender documentation, there may be statements which say thicknesses of fire protection proprietary materials are based on these temperatures. It's for the structural engineer on record to satisfy himself or herself that these temperatures are safe, appropriate, and adequate for the building. I'm not sure how many times structural engineers actually go back and check that. So let's look at, if you like, a bit of fire protection concepts a bit further. In this case, we're looking at the role of the fire protection material. On the bottom of this graph, I've got time in minutes, and up the side, I've got steel temperature or temperature. The curved dark blue line you see at the top is the ASTM E119 fire, or the furnace fire, if you like, that products are subject to. And if I have some sort of limiting steel temperature, in this case I've highlighted 538, and we leave steel unprotected, you can see there it heats up very, very quickly, and in this case fails in about 10 minutes. So it hits that critical limiting temperature of 538 at 10 minutes. And the role of a protection material is simply to slow down that rate of heating and keep the steelwork relatively cool for the required fire resistance period, in this case 90 minutes. So the architect will typically define the fire resistance period in time, and we would look to the structural engineer to provide information in relation to 538 or a limiting steel temperature. Okay. So fire behavior. Let's look at this a bit closely. Fire is fundamentally a load. If you think of some of the buildings that you design on a day-to-day basis, you may look at all sorts of different types of load cases. Ultimate limit state, serviceability limit state, perhaps deflection is controlling, wind is a big load type, snow, depending on where you are, seismic, vibration. There's a number of different checks that we often check our structures against. And my question really is, what about fire? Fire is a load case in its own right, and it has its own load combination. And we do an awful lot of good work with respect to other load cases, but for some reason fire always seems to be put on the back burner, if you pardon the pun. And I've illustrated that with a simplified, let's say, tall building there. And if I take the role as a structural engineer and I say I'm going to design my structure for a wind loading, which is the most severe wind ever recorded on Earth, and I'm going to apply that from the bottom of the building right to the top of the building and design my steel frame based on that. What's going to be the answer or the solution? I'm going to end up with a horribly over-designed, inefficient, expensive frame. Okay? It's going to be very expensive and totally inefficient. But yet that's exactly what we do when it comes to fire. we assume worst case, critical, fully developed fire in many situations to occur simultaneously across an entire floor plate or across an entire compartment, and then we assume that to be the worst case. The reality is, it might not be. If we start to look at it on a case-by-case, on a building-by-building basis, in many cases, it's not as severe as that. So it's all about fire engineering. This is the subject, if you like, of this whole webinar. And I said before, fire engineers may work on a project and look to reduce a fire resistance period, say from 2 hours to 90 minutes, 3 hours to 2 hours. And they do that by looking at how fires grow. And I've put some of the aspects which they'll consider when they do that. They'll look at the fuel load. They'll look at what is actually at risk of burning in the building itself. They'll look at the room geometry. Are we looking at a very small, cramped, enclosed space, or is it a very large, expansive floor plate with very high ceilings? They'll look at ventilation conditions. Are we looking at a masonry or brick type building with very small windows? Or are we looking at modern construction which likes to employ a lot of glazed facades? In the event of a fire, if those facades break, then the ventilation conditions completely change, and that will influence how a fire might grow. And is there a sprinkler system? That might actually help to control the fuel load. And I've put a question there, is this structural fire engineering? Yes, it is in a way, but it's not involving any structural analysis. It's defining the load for a structural analysis, if that makes sense. And whenever a fire engineer looks at this and modifies or proposes to modify a reduced fire resistance period, then it's always subject to approval by the authority having jurisdiction. So, design fires. Let's take a little bit of a look at these now. The graph that you see in the bottom, we've already touched on that. That's the ASTM E119 standard fire curve. So this is what we expose assemblies to within a furnace. And you can see some pictures of a typical furnace on the left-hand side there with some structural elements within it. And it aims to try and create a uniform temperature prescribed by that curve for the required duration of the test. And you can see in the top right there's a picture of a tested assembly being subject to high temperature. So that's one design fire. But fundamentally, that design fire was always intended to test different assemblies and different products with respect to each other. It wasn't necessarily trying to achieve a realistic fire. It was trying to achieve a worst case, fully developed post-flashover fire. The fire engineers may start to look at things in a little bit more detail. And I've put some things here in terms of localized fire or a fully developed fire. A fully developed fire is when everything in the room is ignited and burning, and you almost get a simultaneous temperature acting everywhere within the compartment. It's considered by many to be the most severe type of fire, but it doesn't necessarily mean that it would be the most severe response of the structure. We'll look at that a bit later. So a localized fire, this could be a trash can or a sofa or some localized portion of fuel. And fire engineers have the ability, based off empirical calculations, to work out, based on the diameter or the size of that fuel, how high flames might get and for how long it might burn. And those flames may either impact the ceiling, in which case the figure on the bottom right shows flame lengths and temperatures that can be estimated, or it may not. It may just grow in like a conical or pyramid type shape, and then radiation heat may start to affect the structure surrounding it. Or fire engineers may step it up one more level, and they may start to look at something a little bit more complicated with respect to numerical modeling. In this case, we're looking at CFD, which stands for computational fluid dynamics, and they can work out how fires may grow, how they might travel around a building, but it's worth bearing in mind that any approach like this would need to be fully validated and verified to make sure that it was fit for purpose and was capturing the thermal effects correctly. So let's go back to our standard fire curve and look at it with respect to real fires. I know for a fact that the standard fire curve will go on and on and on forever. Okay? But if we move forward, then what we can do is we can start to look at a real fire, and let's see how that fits in. So in this case, I've got the yellow line, which considered ventilation. I've considered the aspects on the left-hand side, and I've got a fire which grows slightly at a reduced rate to the standard fire, and then it starts to decay. All fires, in reality, will eventually burn out. So we've got a long, cool fire in this case. The alternative to that is a short, hot fire. In this case, it grows very fast. The temperatures actually exceed that of the standard fire, but then the fuel burns out, and then it starts to decay and cool back down to ambient. Okay. So we're looking at real fires in the context of the standard fire. But fire engineers will generally always refer back to the fire resistance period, because at some point we have to match that up with product performance or tested assembly performance. So they say, this is my real fire, how does it equate to reality? And it's a simple energy check. If you like, it's the area under the curve. So I've taken the area under the curve of the red line and equated that to an area under the curve of the blue line. Okay? So what I'm saying is, for that real fire, it's equivalent to approximately 50 minutes in the standard fire. So in that case, if the code had said this building must be a 90-minute building, then we can use this sort of approach to progress discussions to say, why don't we look at considering 60 minutes as opposed to 90? You can't actually physically sustain a 90-minute fire in this building. And what are the benefits of doing that? Let's try and put this into context. What I've done is I've taken a thickness of fire protection for a typical beam or column, and I've looked at it with respect to different fire resistance hourly ratings. So at the top we've got 3-hour resistance and 0.42 inches. If the fire engineer reduces it to 2 hours, then we suddenly drop down to 0.26 inches. That's a drop of 39%. So that's 39% less thickness, 39% less volume of material across an entire project. That's quite considerate. That's quite a big number. When you think of the cost of fire protection and the cost and the time of installing it, a reduction of that level is significant. Every product is different. In this case, when we go from 2 hours to 1.5 hours, the drop's 14%. That's still quite a big number. 1.5 hours to 1 hour, in that case, it's quite a dramatic number, nearly 60%. But it's all based on the product performance and the product thickness at those relevant times. So don't take these as generic savings. This is a specific application, in this case, of an epoxy coating. That gives you an idea of why fire engineers get involved in a project and they look to make savings. It doesn't mean that we've lost any safety. It's still a robust method. It's been quantified, and there's the savings to be had. So we've understood our fire, we've understood our load, if you like. Now we need to know how it keeps up our structure. And there's a variety of ways that it can be done. It's all about understanding the maximum temperature, or the temperature history, if you like, of a structural element. And I've got some examples here using finite element methods with heat transfer built in. And in the case of the two that you see on the left-hand side, they are situations where we have an unprotected steel member framing into a protected member, and that considers the localized hotspot that occurs, which can then be used to have a structural assessment to check load-bearing capacity. On the right side, we've got a steel beam with some sort of assembly on top, and then a fully exposed steel beam. And under different scenarios, you can understand the gradient in temperature that occurs across a steel beam, and then that can be, again, used to inform a structural capacity check at high temperature. And here's an example of, back to our fire that we looked at earlier, that the fire engineer had evaluated using the geometry, ventilation conditions, and fuel load. And if we know the gas temperature or the fire temperature, then there's simple equations that exist in literature and in standards which let us derive the temperature history of steel, so we can understand how steel heats up with respect to a real fire. That can be then input into an FE analysis, and then the thermal expansion of all the members and the thermal contraction and all the interactions at high temperature can be used to inform structural assessment and inform design. So it's deliberately simplified, but it gives you an understanding of how a fire can be considered, and then how that fire can be translated into a temperature on a structural member. So the main aspect now is structural assessment. How do we actually figure out what the structure is doing now that we know it's heating up? Let's go back to our fire protection concept. I said before that it's all about maintaining the limiting steel temperature for a given period of fire resistance, in this case 538 and 90. And we're going to look a little bit more closely at this temperature, this 538, and what can be done with respect to that. So it's all about optimization. I speak to a lot of structural engineers in all parts of the world, and once we get onto the topic of fire protection, then I start to see light bulbs go on as we go through the talk, and they understand what can and can't be done. I've got a simple example here of what can be done. I've got cost against weight of steel member. So if I have two steel sections in my hands, one in my left hand, which is a thick bar, a very thick steel member, and one in my right hand, which is a very thin rod, or a piece of wire, let's say, and I heat them both up to the same rate. The one that's in my right hand, the very thin wire, that's going to burn my hand first. Okay? It's very thin, it heats up very quickly. The thicker member, that's going to take more time to heat up before it burns my hand. So the thicker member has an inherent fire resistance that's greater than the thin member. So let's look at this graph with that in mind. I've got weight of steel member on the bottom and cost. As I put more weight into that member, so I make the web thicker, or the flanges thicker, or the wall thickness thicker, of course that's more steel, the cost of steel goes up. You can see that in the blue line. That's not rocket science. However, look at what it does to the cost of fire protection. It can be a dramatic decrease. And the reason for that, again, is because a very light member requires a lot more protection to keep it cool than a very heavy member. And just about every structural engineer I know often aims for the bottom left-hand corner of that graph to make the lightest, cheapest, most efficient steel frame with respect to cost. The problem is that can create a real big issue when it comes to fire protection. You can get excessively thick material requirements, which are expensive and take a long time to apply. And I often do a lot of work with engineers where I talk them through this, and we play up and down the range of weight to understand the most optimum solution with respect to cost. Cost being steel plus fire protection material plus fire protection application. And once you've got a handle on all those three, then you can really do some special optimization. Okay. So what codes and standards actually permit us to do this approach? It's not all academic theory. It is actually written down and it can be fully referenced. So I've put a list of frequent ones that I come across certainly in the industry. British standards, there's a specific standard for looking at structural fire design, as there is in the Eurocodes, as there is in the AISC standards. Okay. I've also put some ones underneath that, the ISO, ABS, API standards. These are more associated with the oil and gas industry, so some of you may have an awareness of those if you work in that industry. But they also make reference to structural fire design. And in many cases, they actually refer back to AISC standards or to Eurocodes. So the three that I've highlighted in bold there are probably the three most common structural fire standards that I come across within the industry. Right, so let's look at this limiting steel temperature that I've mentioned several times up to now. I put a definition there, and that is that it's the temperature the steel can reach while still maintaining enough strength to carry the applied load. Many people say to me, is it the temperature which the steel frame gets to and then the building suddenly collapses? The answer to that is no, it's not. It just starts to lose strength and it starts to potentially lose stability. And once you understand what the temperature is, you can then use that to inform how much passive fire protection is actually required and whether it's actually needed at all. Fundamentally, it's a function of the applied load. So I say to engineers, I know you can all design buildings at ambient. I know you can all do the hand calculations or you can use the software, and I know that you're all capable of doing this. I say if you can do it at ambient, there's no reason why you can't do some sort of structural fire assessment. I put down there checks, for example, tensile or buckling resistance, moment and shear resistance, or lateral torsional buckling resistance, if that's to be checked. These are all things that we repeat at high temperature. When it comes to beams with web openings, as you can see from the example at the bottom now, they've got a few more modes to consider with respect to failure. And when you start to look at what we call the web post, which sits in between the holes, then you get different failure modes with respect to web post bending, buckling, horizontal shear, veer and deal checks around the openings, what we call top T bending above the openings, in addition to the global bending, global shear, and checks that you might normally consider. And we are starting to see some of these become more common across North America. It's worth pointing out that these types of steel constructions are used on just about every single building here in London because it lets people route the services through the holes, through the openings, and not have to make provision for a service zone below the bottom web. And for every 10 stories that you actually use these for, if you've got a height limitation, you actually gain an extra story on top because of that. However, when it comes to fire protection and understanding fire resistance of these, they're very complex members to actually check, and all the more reason for doing a structural fire check to make sure that they're safe for use. We do see some of these across North America, and I'm conscious that they're referred to as smart beams or other terminology. So looking at AISC and the CSA equivalent, there is an appendix in each of those documents called their Structural Design for Fire Conditions. So if you've not had a look at this, hopefully after this webinar, you'll have a bit of an idea of what can actually be done for these. The load case there, you can see 1.2 times D plus load effect from an extraordinary event, and then perhaps 0.5 times live or 0.2 times snow. I'll let you have a look at these load combinations in your own time, but just to make you aware they do exist. Okay, so we've talked about this limiting temperature approach, and you see this number 538 used very frequently. And it's worth understanding where this actually comes from. And I've done a lot of research to try and find this out, because I know how all the other temperatures around the world are derived. This one I thought I'd pay a bit more attention to. I looked at the SFPE handbook, the Society for Fire Protection Engineers, and they have a statement and a section in there which explains it. And it proposes that it's based on a 60% reduction of yield strength. So what you can see in this graph is how yield strength and stiffness both drop off and lose their capacity with temperature. Okay, so I've got a strength retention factor which you can equate, if you like, in a simple manner to amount of stress acting on a member. So if I use allowable strength design and I say my member is not permitted to exceed 60% of its stress level, and I draw a line across, then you can see the temperature intercepts for yielding at 469 and buckling at 550. And for a column or a member in compression, it's going to be a combination of yielding and buckling, and really 538 is about right. It fits right in between those two. The SFP handbook, incidentally, does state that 538 is based on a 60% reduction of yield strength, which, if you do look at the graph in my book, would actually be 469. But I would consider that to be very, very onerous. So these are very similar strength retention factors, and these are actually given in the AISC and current CSA standards. They're very similar, if not almost identical, to the Eurocode retention factors, and they're based on strain limits in the steel for 2%. The first thing to notice is that the buckling and the yielding have actually swapped over, which I would agree with, in that you're likely to get a buckling before you get a full yield within your structure. But adopting the same principle, you can see there the temperatures of 470 and 559, and somewhere in between that, you're going to get a compression member failure, a buckling failure of around about 538. So that's the simple derivation of where 538 comes from. 538 assumes a member to be fully stressed to its design limit, and it tries to maintain structural stability because of that. But it's quite evident that if you're not working at that 60% stress limit, if, for example, vibration dictates or deflection dictates in design, you might only be operating at maybe 20 or 30% stress levels or utilization. And if that's the case, doing a similar exercise where you read across this graph and down, in the case of 20%, it could be arguing for temperatures around about 700 degrees. So you can justify why it shouldn't be 538, why it could be 600 or 700 degrees. And when you do that, that permits you to then reduce the thickness of material for fire protection. So it's all about stress in structural members. And again, just to illustrate that same concept, I've got a beam on top which is capable of withstanding a certain applied load. So if we take that applied load into scenario A, I said there the beam's loaded to 100% of its ambient design capacity. That's going to induce a deflection and some level of stress in the member. It's going to fail at a certain temperature. And to ensure that that temperature is maintained, it's going to need quite a bit of protection. However, if you look at scenario B, the load is a lot more reduced, the deflection is a lot less, and the relative thickness of protection then goes down, because that beam is allowed to get hotter than, let's say, the 538, and therefore you don't need as much protection. So let's have a quick look at rated designs. Okay, so when we look at building codes, it may say a tested assembly in accordance with UL 263. So then we can dive into a rated design and pick something. But it's important to understand that whatever's chosen actually aligns with the need for the fire resistance of the project. It's appropriate to any structural fire engineering proposal, and everyone understands its limitations as to what it can and can't do. So here's a typical listing table. This is for a proprietary product, and there's a list of steel sections that you see in the left-hand column of the table. So you can see all the W-shaped sections. And then for 1 hour, 1.5, 2, and 3 hour ratings, it gives a thickness of protection. Okay, that's fine. It gives you a thickness, and that thickness will be with respect to 538. And that's how the majority of fire resistance listings are done across North America. However, if we look at the next slide, this is an example of what a table would look like in other parts of the world. And I put it up there because it's for information. It gives you an appreciation of what is done outside of North America and how that facilitates, if you like, a structural fire engineered approach. In this situation, we've taken a British standard test, and we've taken the exact situation that we looked at before for the listing. Down the left-hand side, is what we call a W upon D ratio, which is essentially the size of steel member. And across the top, you can see different temperatures ranging from 687 degrees Fahrenheit all the way up to just over 1300 degrees Fahrenheit. So for each section, in this case I'm looking at a four-sided column, so a column exposed to fire on all four sides at a duration of 120 minutes. And for each section size, there's different thicknesses with respect to failure temperature. So as a structural engineer, I can work out what temperature the steel work will fail at, and then I can pick a thickness relevant to it. And this is how fire protection thicknesses are often derived outside of North America. At present, the ASTM E119 only prescribes a single point failure, if you like, for beams 593 Celsius or for columns 538. So a structural fire engineering assessment can be done. You can work out at what temperature the steel will fail, but you would need, if you were to do that approach, to look at an alternative fire test which is permitted by IBC to justify a thickness relative to that temperature. So some quick examples. Let's have a look at these. Split it into three examples: fire engineering, structural engineering, and structural fire. So let's look at the first one. In all cases, we start with a 2-hour rated column, and I've taken just a generic European-based 500 degrees Celsius. I've looked at a coating thickness of an intumescent coating as an example. So to keep that 2-hour column below 500 degrees, I need 3.4 millimeters of paint. In the fire engineering case, a fire engineer comes on board and justifies a reduction from 2 hours to 1 hour. That drops the thickness to 1.8 millimeters, a saving of 45%. Great. Then we go to what I would call the structural engineering approach, where it's again a 2-hour rated column, but we maintain the 2-hour time period, but we work out the failure temperature with respect to applied load. In this case, it goes from 500 up to 653. That lets us drop the thickness from 3.4 to 1.78. That's a saving of 47% on material. The first approach, the fire engineering one, is subject to the authority having jurisdiction. It can be quite an in-depth engineered approach, a lot of calculations, a lot of reporting, a lot of work, and potentially quite an expensive approach. The structural engineering concept, in this case, is actually saving a greater amount on material, but it's a very, very quick structural check. It can be done as a hand calc even. However, the important thing to note is that the two can be done in combination. And this is where the structural engineers and the fire engineers, when they speak together, can be very, very powerful. The third one is the structural fire engineering approach. And in that case, the fire engineer has reduced it from 2 hours to 1 hour, and the structural engineer has demonstrated that the temperature of the steel can be increased from 500 to 653. And in this case, that's brought the thickness from 3.4 millimeters down to 1.15, saving of 66% material. That's quite a lot. That's a big cost. If you imagine 66% material thickness on a column, multiply that by the number of columns in a building, multiply that by the number of floors in the building, it starts to become a big saving. In this case, it also brought the thickness from a 3-coat system of intumescent down to a 1-coat system. So the application was faster, the constructability was faster, reduced time on site, or greater control if it's done off-site in shop. Okay, so let's look at the other one. I mentioned removal of secondary members. In this case, the image in the building shows a protected bay. All protected members between columns are applied with a proprietary material, but in the middle they're left unprotected. And this is an approach which relies on tensile membrane action. So under high deflection, the slab actually holds those members in place, and very little contribution in terms of stability is gained from those intermediate members. And you can justify this using approaches using either FE or slightly advanced spreadsheet approaches. And this sort of work is done very, very frequently across the UK. And what sort of benefit does it bring? Well, in this example, it's the same approach. You've gone from a fully protected bay on the left to one on the right, where the secondary members are left unprotected. You'll see that there are temperatures on the left-hand fully protected bay, 583, 628. And when we suddenly remove protection from the intermediate members, we lose their load-bearing capacity, and the forces get redistributed out to adjacent members. More force means lower temperature. Okay? So in this case, you can see the beam at the top has dropped from 583 to 440. So that beam's working a lot harder as a result. So therefore, beam A might need more protection, as might beam C. However, you can justify total elimination from beam B. And how much can be saved by doing this? So I've looked at that same bay, but multiplied up 4 across, and then, if you like, 4 or 5 down. And you can see in that graph there, I've got a number of bays, and then potential saving in material by doing that approach. And in this example, material savings of up to about 30% are actually possible. And again, this is employed on a lot of large frame, iconic high-rise buildings here in the UK. And it's also done in New Zealand quite extensively. Okay, final example before we start to summarize and finish up. Here's a quick design, structural engineer's approach on the top, fabricator's proposed design underneath, and then what I would call a structural fire engineer solution on the bottom. The fire engineered solution ends up with the cell spacing quite wide apart, and it ends up by bringing more steel, if you like, into the design. And the next slide is probably best to summarize this up. The original design is on the right-hand side, and it shows the web openings. So this is the structural engineer's design, and I've put this with respect again to weight and cost. So we start off with our norms of 100% on each. The beam at the top was actually proposed by a fabricator as being lighter, more efficient, lots of openings. And in doing so, the cost of that beam actually went up by about 8%. Yes, it saved about 9% in weight, but it became more expensive. And then when he sat with a fire engineer and said, why is that the case? He ended up with the optimum solution, where the structural fire engineer changed the structural design, looked at the thickness of fire protection, looked at the number of coats to achieve that, and then looked at the cost of steel, together with the cost of fire protection, together with the cost of application. And when you combine all of those, then playing up and down this weight scale becomes quite important. So we went from the structural engineer's original design to a lighter, more structurally efficient but very expensive solution, back down to a more structural fire engineered solution, which was of benefit to the project. Okay, so I hope that's given you a little bit of an overview of what can and can't be done. We looked at simple fire resistance ratings all the way through to more complex issues. I just put a list of further information that I can let you peruse and read in your own time. So if we summarize and finish up, then we've looked at structural fire engineering, we've looked at the markets of where it is and where it's not done. It's generally a performance-based design which is permitted by code, and it's all about understanding your fire, understanding how it heats and impacts the structure, and what the structural response is. It's used extensively around the world, but perhaps less so at present in North America, but there's plenty of case studies to look at. There is a big demand for this across the entire contract chain. Obviously, there's different drivers as to why that may be done. I see an increasing engagement with structural engineers and a willingness to now consider hot design. They can be done using simple checks, or with the help of a fire engineer, more advanced methods can be done to bring extra savings. The AISC guidance standards do actually have ways to permit and allow this, but be aware that at present, ASTM typically doesn't always use a variable temperature to look at different thicknesses for steelwork. Always engage with authorities having jurisdiction if you want to look at an aspect of structural fire engineering. And the last slide, really just to sum up, structural fire engineering and the codes that associate with it do allow designers to exploit the properties of structural steel to its maximum at the fire limit state. If used effectively, it can bring significant benefits to a project to put their robust and safe designs, which is always paramount, quantified structural performance instead of assumed performance, and invariably cost savings do fall out of this approach. Yes, fire engineers have the ability to assess performance in fire, but so do structural engineers, and even more so when they engage with a fire engineer. And the last two thoughts I'd like to leave with you are that the first one, fire should be treated as an important load case in its own right, just as wind, vibration, or snow might be, and that fire protection should not be an afterthought of design, because that's when problems can arise. The earlier that it's brought into the design stage, the more benefit it can bring to a project. Thank you very much.
Thank you, Alan, for that was an excellent presentation. We do have a few questions that perhaps you can answer. I'm going to navigate us to slide 70. We have a question about the membrane action here. Presumably the membrane action would increase the connection forces. Does that often control or influence the design?
Oh, absolutely, yes. No, the connection forces are absolutely critical in these ones. We tend to see engineers who do this approach use FE models where they'll actually have a representation of the connection being considered, which again has properties which change with respect to temperature. For example, if it's welded, there are weld reductions with respect to temperature. If it's a bolted connection, then bolts have their own strength reduction with respect to temperature. So yes, sometimes additional features may be required for the connection or changes to the primary members, or with respect to the reinforcement in a concrete slab, there may be a requirement to increase the reinforcement level above some of the primary members to make sure that rupture doesn't occur.
Okay, thank you. I'm going to take us to slide 32, where you reference the ASTM E119 standard. The question is the fire hose test used in standards other than this E119? And perhaps for those that aren't familiar with the fire hose test, maybe you could just briefly explain what that is.
Yes, the first part of that question is it's predominantly in North American tests that we see the requirement for a fire hose test, which is after a fire has occurred, can the assembly withstand the cooling and contraction forces, if you like, that occur on subject or on application of water as a result of firefighting activities. It's predominantly in North America that we see that requirement, although I recognize that it's a very important situation, especially when firefighters are requested to go in and suddenly change the thermal environment of the structure. But no, it's primarily North America standards that require that.
Okay, thank you. The next question is, how does the International Code Council, ICC, recognize fire design?
It's a good question. Good question. A lot of people look at fire design, and I mentioned it in the presentation. They'll say, oh, it's not something you can do. It's not something that's accepted in North America. But there are numerous cases which can be referenced, and I know that even some of the people on this call, I think, will have experience of doing a fire engineered approach with respect to structures in North America. If you look at the IBC, it does state that alternative methods to demonstrate fire resistance can be done. There's nothing stopping you putting forward a proposal, providing that you can demonstrate the intent of the ASTM E119 test is maintained, and that as long as the authority having jurisdiction is happy to accept and review those calculations, there should be nothing stopping you effectively proposing that sort of approach. And I know it is done.
Okay, great. Thank you. Our next question is, Uh, is this structural fire engineering approach economical in all cases, or are there certain building types that would benefit from this?
That's a very good question. It's worth pointing out that invariably, yes, a cost saving does come. It's also worth pointing out that in some situations, you may identify that the provisions given by the standard approach, let's say, may not even be adequate. You might have to do something above and beyond the codified, deemed to be accepted approach. That's obviously quite rare, but it does happen now and again. In terms of what is best for this approach, we find that office buildings, high-rise buildings which have a high fire resistance period, they often contribute the biggest cost saving. If you've got a low structure which only needs, say, 15, 20, 30 minutes or 60 minutes in some cases, they won't always necessarily give you the most optimum benefit when you start to look at it, unless you're removing fire protection left, right, and centre in the building. But I would typically say high-rise buildings where you have uniform floor plates, uniform structural layouts, they lend themselves very, very well to this approach.
Okay, thank you. Are there any buildings that are well known that have used this structural fire engineering approach?
There are, yes. There's an awful lot. If you look at the skyline of London, every single tall building on the skyline of London has been subject to a structural fire engineering assessment at one level or another. In other parts of the world, in New Zealand, again, any iconic high-rise building that you can look at, then that would have likely been through an assessment of it. The Shard, if you're familiar with that in London, that's London's tallest building, that had a significant structural fire engineering assessment done where structural engineers worked very closely with the fire engineers and with the authority having jurisdiction in central London to make sure that everyone was happy with the design, and that brought considerable cost savings and construction sequencing benefits which benefited the project to a great extent.
Okay, great, thank you. Well, that is all the time we have for questions. If you did not get your question answered today, we'll work with Alan and to get a response and then try to reach you by email. So as a reminder about CEUs, within 2 business days you'll receive an email with instructions on how to obtain CEUs for everyone at your connection. Please follow the information that will be provided in the forthcoming email from registration@aisc.org. And if you're interested in more opportunities with AISC's continuing education, we have a few opportunities coming up. We have 3 webinars that are part of our night school course on composite floor design. These 3 webinars will be on the topic of floor vibration and will be presented by Dr. Tom Murray. You can find more details at www.aisc.org/nightschool. And for those of you in the New York City area, we have an in-person seminar next week on June 11th on the Seismic Design Manual. This seminar will focus on special concentrically braced frames and special moment frames, and this will be given by Dr. Tom Sable. You can find out more information at aisc.org/seminars. Please help us out by completing our survey form that will pop up on the screen immediately following the webinar. It's very short, so please fill it out. We greatly appreciate your feedback. And a special thanks to Alan Jauzi in providing today's presentation. Thanks again for attending the webinar. Have a good day.